A hearty welcome to all. I am Hm-Noufiya, Industrial Engineering 2019-23 batch of CET. Here my assigned work is to discussing a problem on Kaplan turbine. Before going to problem, I am reminding something that the turbine in which water flowing parallel to the axis of rotation of shaft is known as axial flow turbine. The important type of axial flow turbines are propeller turbine and Kaplan turbine. Here I am discussing the Kaplan turbine. The important points for Kaplan turbine are: first one, the peripheral velocity at the inlet and outlet are equal. That is U1 equal to U2, which is equal to pi d naught into n by 60, where d naught is the outer diameter of runner. Second point is velocity of flow at the inlet and outlet are equal. That is Vf1 equal to Vf2. So these are the important points for solving the problem. Now I am moving to the problem, and the problem is: a Kaplan turbine working under a head of 20 meter develops 12,270 kilowatt shaft power. The outer diameter of runner is 3.5 meter and the hub diameter is 1.75 meter. The guide blade angle at the extreme edge of runner is 35 degree. The hydraulic and overall efficiencies of turbines are 88% and 84% respectively. If the velocity of whirl is 0 at the outer diameter, first one, determine the runner-vane angles at the inlet and outlet at the extreme edge of runner and the speed of turbine. So before going to solve the problem, we have to write the given terms as head, that is H is 20 meter, shaft power SP is 12,270 kilowatt, outer diameter of runner, that is D naught is 3.5 meter, hub diameter, that is dB is 1.75 meter, guide blade angle, that is alpha is 35 degree, hydraulic efficiency, that is theta h is 88%, and the velocity of whirl at the outlet is 0. So we have to draw a neat sketch regarding these terms, and I am considering two triangles, that is inlet triangle and outlet triangle. At the inlet triangle, that is guide blade angle alpha is 35 degree, runner vane angle at the inlet, that is theta, u1 is the peripheral velocity at inlet, vw1 is the velocity of whirl at inlet, vf1 is the velocity of flow at inlet, vr1 is the relative velocity at inlet. And in outer triangle, phi is the runaway angle at the outlet, Vf2 is the velocity of flow at the outlet, U2 is the peripheral velocity at the outlet, and Vr2 is the relative velocity at the outlet. Here Vw2, that is velocity of whirl at the outlet, is 0, which is given in the question. Now we have to solve the problem. First of all, we have to find the value of Q, that is discharge. For this, I am using the equation for overall efficiency, that is eta naught, which is shaft power by water power. Here water power Wp is rho g QH by 1000, where rho is the density of water, g is the acceleration due to gravity, Q is the discharge, and h is the head. By substituting the values of eta naught as 0.84 and shaft power as 12,270, density of water as 1000 and g as 9.81 and head as 20, we have to rearrange and solve. We get the value of discharge as 74.45 meter cube per second. Also, the equation for discharge is area into velocity, that is here area is pi by 4 into d naught square minus dB square, and velocity is Vf1, that is velocity of flow at inlet. By substituting the value of discharge, that is Q, as 74.45 meter cube per second in this equation, we get the value of Vf1 as 10.33 meter per second. From this triangle, that is inlet triangle, we get tan alpha as Vf1 divided by Vw1. By substituting the value of Vf1 and tan alpha as tan 35, we get the value of Vw1, that is velocity of whirl at the inlet, as 14.75 meter per second. Using the equation of hydraulic efficiency, that is eta h, which is Vw1 u1 divided by gh, and substituting the value of eta h as 0.88 and VW1 as 14.75, G as 9.81 and H as 20, we get the value of peripheral velocity at inlet, that is U1 as 11.705 meter per second. By using these values, that is U1, VW1 and VF1, we can find the runaway angles at inlet and outlet. For this, we have to consider this triangle. Here, tan theta is Vf1 divided by Vw1 minus u1. So we have to substitute the value of Vf1, Vw1 and u1 as 10.33, 14.75 and 11.705. We get tan theta as 3.39. Then theta as 73.58 degree or 73 degree 34 minute. But in Kaplan turbine, the peripheral velocity at inlet and outlet are equal. That is U1 equal to U2, which is equal to 11.705 meter per second, which is already calculated. And also the velocity of flow at inlet and outlet are equal. That is Vf1 equal to Vf2, which is equal to 10.33 meter per second, which is also calculated. From the outlet triangle, that is this triangle, tan phi as Vf2 by U2. By substituting the value of Vf2 and U2 as 10.33 and 11.705 respectively, we get tan phi as 0.88. Then phi as 41.43 degree or 41 degree 25 minute. Then we get the runaway angles at inlet and outlet as 73.58 degree and 41.43 degree respectively. Next, we have to find the speed of turbine. Here we are using the relation U1 equal to U2, which is equal to pi d naught into n by 60. By substituting the value of peripheral velocity as 11.705 and d naught as 3.5, we get the speed of turbine, that is n as 63.90 rpm. Hope you all understood this problem and thank you for watching.